All right, let's go.
Number 9. The methane that appears and disappears. This one started in 2003 and it is still not resolved. Methane is a simple molecule, 1 carbon atom, 4 hydrogen atoms. On Earth, it is produced almost entirely by living things, cows, wetlands, microbes. About 95% of all methane in Earth's atmosphere comes from biological processes. In 2003, ESA's Mars Express Orbiter detected methane in the Martian atmosphere. Then, ground-based telescopes confirmed it at levels up to 33 parts per billion in some regions. Then, NASA's Curiosity rover landed in Gale Crater in 2012 and spent years measuring the air around it. Background methane of about 0.41 parts per billion, with episodic spikes, one night in June 2019 shooting up to 21 parts per billion before dropping back the next day. In Mars's oxidizing atmosphere, methane should not survive long. Photochemistry should destroy it within about 300 years. The fact that it exists at all means something is producing it right now, either geologically, serpentinization, where water reacts with certain rocks to produce methane, or something biological. Then ESA's Trace Gas Orbiter arrived, specifically designed to measure methane at far higher sensitivity than anything before it. It should have detected any methane at levels above 0.02 parts per billion globally. It found nothing, not a trace. A 2025 paper published in the Journal of Geophysical Research by Sebastian Viscardi and colleagues proposed one possible explanation. The methane Curiosity detected may be leaking from inside the instrument itself. The TLS spectrometer Curiosity uses sits in a chamber where methane concentrations could be artificially elevated by contamination. Not Mars methane at all, just instrument methane. This has not been confirmed. It has not been ruled out. The debate is so unresolved that as of 2026, scientists cannot agree on whether methane on Mars even exists. The most important gas in the search for life on Mars might be a measurement artifact, or it might be venting from something alive under the surface. No one knows which.
Number 8. The oxygen that no one can explain. Methane was mystery enough. Then Mars gave us another one. In 2019, Curiosity measured for the first time the seasonal variations in every gas directly above the surface of Gale Crater. What it found was expected for most gases: carbon dioxide rising and falling as dry ice caps at the poles sublimated and refroze, argon and nitrogen behaving predictably, seasonal patterns fitting known models. Then oxygen. Every spring and summer, the oxygen in the Martian atmosphere rises by about 30% above the expected level, then drops back down in autumn. The same pattern, every year. Nothing in current atmospheric chemistry explains it. On Earth, seasonal oxygen cycles are driven by photosynthesis. Vegetation absorbs carbon dioxide and releases oxygen during growing seasons. Mars has no known vegetation. It has no obvious biological mechanism for this cycle. Abiotic explanations have been proposed. Hydrogen peroxide or perchlorate salts in the soil releasing oxygen when heated by seasonal sunlight. But the calculations do not produce oxygen increases large enough to match what Curiosity is measuring. Either the models of Martian soil chemistry are wrong, or something unknown is producing that oxygen, or possibly something biological. As of 2026, there is no accepted explanation. The oxygen cycle on Mars is unresolved.
Number 7. The Leopard spots that might be life. This is the most recent mystery and the most significant. In July 2024, NASA's Perseverance rover was exploring the Bright Angel Formation in Jezero Crater when it drilled into a rock nicknamed Chayava Falls, a reddish mudstone from an ancient river valley floor. The sample it collected was designated Sapphire Canyon. The rock contained organic carbon, minerals including ferrous iron phosphate and iron sulfide, and a pattern of small spots ringed by darker halos distributed regularly through the rock. Scientists called them leopard spots. On Earth, this exact pattern, organic carbon with iron sulfide and phosphate minerals arranged in ringed spots, is produced by microbial metabolism. Microbes create redox gradients in rock. Energy flows along those gradients. Minerals precipitate in specific patterns around the biological activity. The leopard spots are one of the recognized signatures of microbial processes in Earth geology. NASA published the findings in Nature in September 2025. The paper, led by Joel Horowitz at Stony Brook University, was careful. Abiotic explanations exist: hydrothermal reactions, redox gradients without biology. The paper concluded that abiotic explanations are less likely given the full pattern of evidence, but they cannot be ruled out. NASA's acting administrator called it the closest we have ever come to discovering life on Mars. The sample is sitting in a sealed tube on the Martian surface right now. Mars Sample Return, the mission that would bring it to Earth for analysis in laboratories with instruments far more sensitive than anything a rover can carry, is in flux as of 2026. Its scope and timeline are uncertain. The one sample that might answer the most important question in the history of exploration is on Mars. We do not yet have a confirmed plan to bring it home.
Number 6. The lost magnetic field. Today, Mars has no global magnetic field, no protective shield against the solar wind. Charged particles from the sun stream directly into the Martian atmosphere continuously, stripping it away, molecule by molecule, over billions of years. But Mars did have a magnetic field once. The evidence is in the rocks. The southern crust of Mars is strongly magnetized. The rocks there were magnetized when they formed, which means Mars once had an active planetary dynamo, a liquid metallic core generating a global field the same way Earth's does today. That dynamo shut down. The field died, and without it, Mars could not hold its atmosphere. The magnetic field on Mars is not symmetric. It covers primarily the southern hemisphere. The northern hemisphere has very little crustal magnetization. The large impact basins, Hellas, Argyre, Utopia, Isidis, show almost no magnetization at all. This means the dynamo had already died before those impacts occurred, around 4 billion years ago. Why was the field only in the south? A 2025 paper from the University of Texas Institute for Geophysics presented a new model. Their simulations showed that if Mars's core was still partially molten, not the fully solidified inner core Earth has, the dynamo could have operated asymmetrically, concentrated in one hemisphere, producing the one-sided crustal imprint we see. But why did the dynamo die so early? Mars is smaller than Earth. It cooled faster. Its core solidified. The convection that drives a dynamo requires a liquid outer core around a solid inner core, exactly like Earth's. Mars no longer has that. InSight's seismic data found no evidence of a solid inner core in Mars. The whole core may be liquid, a different state entirely from Earth's, one that may not support long-term dynamo activity. Why Mars's dynamo lasted as briefly as it did, why it was asymmetric, and why it died while Earth's has continued for billions of years, none of this is fully resolved. Number 5. Where did all the water go? Mars today is a desert, thin, cold atmosphere, no liquid water on the surface, average surface temperature of minus 60 degrees Celsius, no rain, no rivers, but the evidence that it was once radically different is everywhere. Valley networks carved by flowing rivers cover large portions of the ancient southern highlands, delta deposits where rivers once entered lakes, rounded pebbles in Gale Crater that Curiosity found, only formed by water tumbling rocks together over long periods. Perseverance's ground-penetrating radar confirmed in January 2024 that Jezero Crater held a vast lake and a river delta that filled and drained multiple times over billions of years. About 3 to 4 billion years ago, Mars was warm enough and wet enough for liquid water to flow on its surface for extended periods. Then it stopped. Some of that water is still there, frozen in the polar ice caps, locked as permafrost below the surface. NASA estimates an equivalent of a global ocean 35 meters deep could still exist as subsurface ice. In 2018, ESA's Mars Express radar detected what appeared to be a subglacial lake beneath the south polar ice cap, liquid water kept from freezing by high salinity and possibly geothermal heat. Further analysis complicated the picture. Multiple bright radar reflectors were found, some in locations where liquid water should not be possible given current heat flow estimates. What evaporated the surface water? The magnetic field collapse came first. Without it, solar wind erosion accelerated, the atmosphere thinned, the greenhouse effect weakened, temperatures dropped, water retreated underground or froze at the poles. But the exact timeline, the rate of loss, and how much water might still exist as liquid underground are all open questions as of 2026.
Number 4. The Dichotomy. Mars is two different planets wearing the same name. The northern hemisphere is flat, low, among the smoothest terrain in the solar system. It sits roughly 3 to 5 kilometers below the southern highlands in average elevation. Very few craters. The southern hemisphere is high, rugged, ancient, heavily cratered, the oldest terrain on Mars. These two hemispheres cover the same planet, but look like they have entirely different geological histories. The boundary between them, the crustal dichotomy, is one of the oldest features on Mars and one of the most poorly understood. Two competing explanations have serious scientific support. The first is a giant impact. A single, enormous collision early in solar system history struck the northern hemisphere with enough energy to melt the crust and reset the surface entirely, removing craters, flattening terrain. The impactor would have been roughly the size of Earth's moon. This single impact hypothesis explains the roughly elliptical shape of the northern lowlands. The second is multiple smaller impacts, a period of intense bombardment concentrated in the northern hemisphere rather than one giant hit. A third possibility, endogenic processes. Internal geological forces produced the difference rather than any external impact. Different mantle dynamics beneath each hemisphere, generating different surface conditions over billions of years. All three explanations remain viable. No single model has been confirmed by the available data. The fundamental reason Mars looks the way it does, divided into two completely different worlds on the same planet, is still not understood.
Number 3. The recurring slope Lineae. Since 2011, Mars Reconnaissance Orbiter has photographed dark streaks appearing on steep Martian slopes during warm seasons and fading in winter. Hundreds of them, on crater walls, on canyon slopes, on sun-facing hillsides. They look exactly like what you would expect flowing liquid to look like on Mars. For years, the leading explanation was briny liquid water, salt concentrations low enough to remain liquid at Mars temperatures, hydrated perchlorate salts absorbing atmospheric water and releasing it as brines that flow downhill. The detection of hydrated salts in these streaks was announced in 2015 as the strongest evidence yet that liquid water currently flows on Mars. Then, more careful analysis began to push back. The streaks appear at angles too steep for viscous liquid flow to explain. They extend through fine-grained material and patterns more consistent with granular flow, dry sand and dust cascading downhill, than liquid. The hydrated salts could have been deposited at a different time than the streaks themselves. In 2019, a detailed reanalysis concluded that dry granular flows fit the observed pattern better than liquid water in most cases. As of 2026, the debate continues. Some planetary scientists still argue that briny water is the most consistent explanation. Others maintain the case for dry flows. The recurring slope Lineae remain unclassified. Their cause, liquid, dry flow, or something else, is not settled.
Number 2. Olympus Mons and why Mars grew the largest volcano in the solar system. Olympus Mons is the largest volcano in the solar system, 21.9 kilometers tall, 600 kilometers wide at its base, so wide that standing at the center you could not see the edges. The curvature of Mars would take the rim of the volcano below the horizon. This exists because Mars has no plate tectonics. On Earth, the oceanic plates move continuously. A mantle plume, a column of hot material rising from the interior, feeds a chain of volcanoes as the plate drifts over it. The Hawaiian island chain was produced this way. Each island is the product of a different period as the Pacific plate moved over the same mantle plume. Mars has no moving plates. The crust does not drift. So when a mantle plume rose under one spot on Mars, it kept feeding material into the same location for billions of years, building the same volcano continuously without the crust moving away. The mystery is not why Olympus Mons exists. The mystery is why Mars has no plate tectonics at all when Earth does. Both planets formed from the same solar material. Both have rocky crusts over hot mantle interiors. Earth's plate tectonics emerged early and continued for billions of years. Mars may have had very brief or limited tectonic activity early in its history and then shut down. The leading explanation relates to the magnetic field collapse and the rapid cooling of the Martian interior. Without sufficient internal heat, the convection currents that drive plate motion on Earth simply stopped. But the threshold between a planet with plate tectonics and one without, what determines which outcome a rocky planet gets, is not well understood. We have only two examples in the inner solar system of large rocky planets, one with plate tectonics, one without. Understanding why Mars went the way it did is directly relevant to understanding whether plate tectonics and the carbon cycle it drives is necessary for a planet to develop and sustain life. Number 1. The samples that might answer everything, if we ever get them back. This is not a mystery about Mars. It is a mystery about us. Perseverance has collected 27 rock cores, sealed in titanium tubes sitting on the Martian surface and cached in the rover. They include Sapphire Canyon from Chayava Falls with its potential biosignatures, sediment samples from the ancient delta, rock from multiple geological periods and Jezero crater's history, the most scientifically valuable collection of extraterrestrial material ever assembled by a spacecraft. Laboratory analysis on Earth could measure isotope ratios that distinguish biological from abiotic processes with a precision far beyond anything a rover can achieve. It could search for molecular structures, chirality, the handedness of organic molecules that on Earth are the exclusive product of biology. It could date the rocks within tens of thousands of years of accuracy. It could look for cell-like microstructures. It could do everything the rover cannot. Mars Sample Return is the mission that would bring them home, a joint NASA-ESA effort involving a lander, a rocket launched from Mars, an Earth return orbiter, and a sample retrieval capsule, the most complex interplanetary mission ever attempted. As of 2026, Mars Sample Return's cost has ballooned. Its timeline has been pushed back. An independent review in 2024 found the existing architecture unaffordable. NASA is redesigning the mission. New approaches are being evaluated. Private sector involvement is being considered. The samples are waiting on Mars. The instruments on Earth that could analyze them already exist. The answers may already be sitting in those tubes. Getting them back is proving harder than collecting them. 9 mysteries. Methane that appears at the surface but vanishes from orbit, possibly life, possibly geology, possibly an instrument leak. Oxygen that rises 30% every spring with no known source. Leopard spots in a rock that look exactly like what microbial life leaves behind. A magnetic field that died in one hemisphere and left the other unprotected. An entire ocean's worth of water that vanished into ice and thin air. 2 completely different hemispheres on the same planet with no agreed explanation for why. Dark streaks that may or may not be liquid water flowing on a world where liquid water should not exist. The largest volcano in the solar system built by a planet that never developed moving plates. And 27 rock cores sitting sealed on the Martian surface that might answer all of it, if we can find a way to bring them home. We are closer to understanding Mars than we have ever been. We are also further from definitive answers than anyone expected. Subscribe to Cosmic Hives. See you in the next one.